Okay, so this is a video to watch on heat. It's from chapter 10 of the whole text. So the first thing I want to look at is temperature. So simple definition of temperature is the average kinetic energy of the molecules. So if something has a higher temperature, that means that the molecules have higher kinetic energy, thus they are moving more rapidly. The higher velocity, in a sense. And if you remember, kinetic energy is 1/2 mv squared. So something that has higher temperature means that the velocity itself must also be higher. The velocity of the molecules, meaning they're vibrating at a higher rate. The easy way to think about this is to think about if you add energy to something, how it changes the actual temperature. If you think about when you turn on like a stove, or if you turn on, or let's say you're using a Bunsen burner, or you have a heating element underneath it, what you're doing is you're adding energy. And when you add that energy, it actually increases the temperature of the object that you're warming up. Another thing to think about is how temperature is really a relative term. And sometimes it's tough to realize this, but an easy experiment, if you go ahead and take, let's see, let me use two colors here. You take one, say, a bowl of cold water, something you could fit your hand in, so maybe like a big Tupperware. Okay, fill it with cold water, put some ice cubes in there, okay? Take another Tupperware that your hand can fit in, fill that with, I don't want to say hot water, don't burn your hand, but hot enough that you can withstand it. So hot tap water, something maybe less than like 120 degrees Fahrenheit. So hot water, but not something that's going to scald you at all. Okay, take the two of them. Place like, let's say let me use a different color here. One of your hands in this cold basin, your other hand in the warm basin. Okay, now, make sure you have a third basin, though, beforehand that's set up with what we'll call lukewarm water or normal room temperature. So like a mix of hot and cold water. So again, you have really cold on the left. You have hot water on the right. Okay, and then this is like room temperature water. Okay, put your hands in there. Place your left hand in the hot water or cold water. It doesn't matter which hand. Place your other hand in the other temperature water for about 15 seconds. Then take them both out and place them in the room temperature water. And think about what happens. You're going to feel a very interesting feeling there. Because this is going to feel really hot at first, and this is going to feel really cold. And then when you move into the room temperature water, you're going to notice something that happens. And that'll maybe help understand that temperature is a relative term. So one thing may be hotter than another. And if we're looking at these two terms, we might say like, well, your right hand felt hot initially because it was in the hot water here, and it felt cold because it was here. But the minute you put it in the room temperature water, you're going to notice something might happen. The next thing to talk about is thermal equilibrium. Now, we've talked about equilibrium before in forces, and with force equilibrium, it meant that the forces were balanced. So, for example, you push against the wall pushes back against you, and there was a balance. You were in a state of equilibrium. With thermal equilibrium, it's similar. We're looking at temperatures, though, now, because, obviously, thermal. Think about an example of hot chocolate. So, you make a cup of hot chocolate. Okay, and you realize it's really hot, so what do? You pour some milk in. And I'll use gray for now. So you take milk and you pour milk into the hot chocolate. And the milk at first is on top. You take a spoon and you begin to stir it up. Well, what's going to happen is it's going to reach some medium temperature. So let's say the temperature of the milk was, for the sake of this, not frozen but cold, so 10 degrees Celsius. Okay, and the temperature of the hot chocolate was near boiling because it had just boiled, so we'll say it's 90 degrees Celsius. What's going to happen is and this is depending upon the mass, obviously, but it's going to reach some temperature of equilibrium that's between these two. So let's say you can drink hot chocolate at a temperature of, I don't know, 55 degrees Celsius. You need to pour enough milk so that this reaches a thermal equilibrium. And you're going to have a balance, and it's just the meanings that the temperatures find an equilibrium over a time period. So what we can say is that as time goes on, as time goes to infinity, the temperature will reach some constant. Okay? So initially it might not right away cool off, or it might not reach that temperature you want it to be, but if you wait long enough, maybe a little while, stir a little bit, the temperature will be constant. Now, don't forget though, eventually it's going to cool down if you leave it out, because the temperature in the room, which is considered our ambient temperature in the room might be even cooler. So the temperature of the room might be about 30 degrees Celsius. So even if this cocoa milk mix reached a temperature of about 60 degrees, eventually, because the room is 30 degrees, if you left it out, it would find an equilibrium temperature as well. So again, you have to think about the system as a whole, not just each individual object. The reason thermal equilibrium is so important is because it really is the basis for measuring any temperature of something. And if you think about a thermometer, what's happening is you're placing the thermometer and it's in contact with the object, right? And that column of liquid in the thermometer rises or falls based on the temperature. Well, if we think about this, the temperature of the fluid inside of the thermometer is increasing. And until that temperature stops increasing to the correct temperature, it's going to keep rising. So we can look at a thermometer now. There's a thermometer bulb at the bottom. Okay, it's filled with this fluid, and usually it's in red. And let's say currently it's filled to here. But then you place this bulb in a cup of hot water, for example. Okay? What's going to happen is this temperature is going to increase, or it's going to read out as an increase until it gets to the temperature of the actual water. So this temperature might be 100 degrees Celsius, so the water's boiling. Whereas earlier, it had maybe started at a temperature of around 40 degrees Celsius, so it was at the room temperature value. Well, this actually leads us into the next thing, which makes us think, well, what makes this fluid rise up in the thermometer? What causes it to move vertically? Well, that's called thermal expansion. So that's the next thing we're going to talk about now. So, thermal expansion simply means that as the temperature of something increases, the matter itself has a tendency to expand. The easiest example I can think of is a bike tire. Or a car tire, doesn't matter. Here you have a tire. And you'll notice that during the winter time, what happens to this tire is it starts to flatten a little bit. Okay, the tire itself is no longer as, you might want to say, pressurized. The volume of the gas inside actually decreases in the cold weather, which is what causes your tires to look like they're flat in the winter. So in the wintertime, the first thing you should always do with your car is pump more air into it. Now, certain gases have different thermal expansion coefficients, and one thing you'll hear nowadays is that you should pump your tires with nitrogen, actually. Because in the winter, the nitrogen molecules do not contract as much. And what you'll see is that if you have oxygen in your tires, they might seem flat. But if you have nitrogen in them in the winter, the temperatures don't get down to a low enough temperature to cause the nitrogen gas to actually contract and to cause your tire to become flat. And vice versa. We can think about a hot air balloon. You know, the hot air balloon, okay, looks like the following. And suddenly you put this torch underneath it. And what the torch does is it heats up all of the air in here, and that air expands to a certain volume, which causes the air balloon to have a less density than air, so it will eventually rise up into the air. So the idea of thermal expansion is simply, as temperature increases, the volume increases. And as temperature decreases, the volume decreases. So there is some direct relationship. Now, before I generalize too much, this is a general statement here, but there are exceptions. And, we talk about how different substances have different coefficients of volume expansions. Generally, gases have the largest value of expansion. So, for example, a gas will expand a lot easier than a liquid will when you increase its temperature. But there is one exception, and that exception is something that's around us every day, and that's H2O. Now, H2O, in its liquid form, we call water, obviously. In its gaseous form, we call steam. In its solid form, we call ice. And you'll notice that when you take ice, or let me start with water, and you put water into an ice tray, what actually happens, and this is interesting to think about, is that the water that fills that ice tray actually expands. Now, that's kind of contradictory to this earlier statement up here. Okay? And this is a little bit of an exception, and it really has to do with the hydrogen bond that occurs in H2O. And I'm not going to go into a lot of detail about that, but just know that this is one of the exceptions. If you lower the temperature between 4 degrees Celsius and 0 degrees Celsius, so at 4 degrees Celsius, H2O is in the liquid form, it's water, and at 0 degrees Celsius it's become ice. And what happens in that range is actually when you lower the temperature, it expands, which causes it to become less dense than water. And you'll notice ice has a tendency to float. Okay, because the ice, or the solid phase of H2O, has expanded, its density has decreased, so it starts to float. Okay, and remember that density is equal to the mass of an object over its volume. So what we're seeing is that the volume is going up, but the mass is remaining the same. So this means that the density of ice, is going to be less than the density of water. And this is also what really causes, a pond to freeze at the top instead of at the bottom. And you see that, frozen layer up top, and in the winter, you want to go ice skating on the top of the ice, but there is water beneath there still, and that's why you have to always be careful. But, this is what keeps fish alive in the winter. If this didn't happen, then, in the wintertime, all the water would freeze and the fish themselves would freeze, but they remain alive underneath that frozen surface. Next, I want to talk about just different temperature scales, and you've heard of these before, but we'll just discuss them real quick. You have Celsius, and you have Fahrenheit. What I'm going to do is actually derive the formula real quick, because I think it is quite important, actually. And what we'll notice is that these are two different scales, and they just measure different increments. That's all it is. One of them comes from really an absolute value, or an absolute zero scale of what. And Celsius, the absolute temperature scale, is called kelvins. And Fahrenheit is called Rankine. And we're not going to get into too much detail about these, but what these measure really is they measure the absence of motion. And 0 Kelvin, or 0 Rankine, really just simply means when an object has no kinetic energy or no motion. And this is actually impossible. And I'm going to talk about why this is impossible in a minute. But these two scales have different increment values. And let me show you what I mean by increment values. If I had a Celsius thermometer and a Fahrenheit thermometer, what you'll see is that on a Celsius scale, from 0 degrees Celsius to 100 degrees Celsius, there's actually a difference of 32 degrees Fahrenheit to 212 degrees Fahrenheit. So what you'll notice is that this is a delta of 100 degrees change, whereas this delta over here is 180 degrees. And if you look at this, you'll say, well, that just means that to move a degree Celsius is the equivalent of more than a degree Fahrenheit. It's actually 1.8 if you look at it. And you could just simply look at the ratio. Okay, this reduces to 9/5 or 1.8. Okay, and now, the easy way to make a conversion between these two is to simply look at these values. So let's take a look. If we look at these four values here, and think of them as coordinate points, 0 associates to 32, whereas 100 associates to 212. And you'll see this if you do any cooking or anything. So let's write these coordinates. So 0 Celsius is really the equivalent of 32 Fahrenheit, and 100 Celsius is the equivalent of 212 Fahrenheit. So we have 2 points, okay, so we can make a linear function between them. As one of them increases, the other increases proportionally. So what we'll see is that we say our slope is delta y over delta x. Remember, y2 minus y1 over x2 minus x1. So we end up with 180 over 100. Again, bringing back the idea of 9/5 from earlier, or 1.8. Okay, that's good. So right now we know that we can say y equals 9/5 x plus b. Well, the question may become, well, what is that b value? Well, to find the b value, remember, all you really need to do is go ahead and plug in one of your points. So let's plug in the easier point. So we're going to take this point here and plug it into the equation, 0 for x and 32 for y. Well, when that happens, you get y equals 9/5, sorry, not y, but 32 equals 9/5 times 0 plus b, which just tells us that b is 32. So the relationship we get is y equals 9/5 x plus 32. Well, you might be saying, how does that help me? Well, think back. This was your y value, which was Fahrenheit, and this was the x value, which was Celsius. So I'm just going to go into this formula now, and wherever I see an x, I'm going to put C for Celsius, or TC for temperature in Celsius. And where I see the y value, I'm going to put TF for temperature in Fahrenheit. And this is the relationship that we use and know. The temperature on a Fahrenheit scale is 9/5 that of the temperature on a Celsius scale, plus our value 32. Now, if we take that exact figured out the other way, sure, we could reverse our x and y and resolve this entire thing, or we can just solve for TC. So let's subtract 32 and multiply by 5/9. So if you're ever given a temperature in Fahrenheit and you want to figure out the temperature in Celsius, you can use this relationship right here. Okay? Again, multiplying by 5/9 to get rid of the fraction. In case that wasn't clear. Whoops. Let's move that back over. Okay? Okay. What I'd like to look at next is that scale that we talked about a minute ago, which we called Kelvin. And there's also one called Rankine, which is not as widely used. We use the metric system, which is the Celsius scale, actually, so we're going to stick with Kelvin for now. What Kelvin means is the following. Kelvin is this. If you look at a Celsius scale, sure, there's 0 Celsius and there's 100 Celsius. We know this to be the boiling point of water, and we know this to be the freezing point of water. And later on, we're going to talk about these as different things. We're going to talk about vaporization and fusion, but for now, let's just load them as that. Now, you might ask yourself, well, surely things can get colder than water. I mean, in the winter, we could say it's below freezing out. You know, what does that mean? It means it's below 0. So 0 is not actually the lowest value. And that's what we want to think about now. And what we actually know is that this can go down a lot further than 0. It can go down all the way down to what we know as right now, 273.15. Okay, and that's negative, obviously, because we're going below that temperature. And this is what we call absolute zero. Absolute zero. And the Kelvin scale is actually an absolute scale. And what that means is that the Kelvin scale, I'm going to put it next to it. I'll superimpose this right next to it. So here's Celsius and here's Kelvin. The negative 273.15 Celsius is where Kelvin starts. This is 0 kelvins. So 0 Celsius is actually already up to 273.15 positive kelvins. This is all the way up at 373.15 kelvins. So what we can notice is this relationship between Kelvin and Celsius. We can say that the temperature in the Kelvin scale is just the temperature in the Celsius scale plus 273.15. And you may ask yourself, well, why is this even important? Why do I care about this Kelvin scale? Well, it's actually pretty interesting to think about. And here's what it means. Kelvin at a 0 temperature means that the molecules have actually stopped moving. And if we remember the definition of temperature to be the average kinetic energy, when the molecules completely stop moving, you have no kinetic energy. If velocity equals 0, then kinetic energy equals 0. Well, if kinetic energy equals 0, then temperature equals 0. Now, there's no such way to actually reach 0 Kelvin, and this is something you have to think about, and it's tough to think about this. The easy way to think about it is as follows. If you want to cool down an object, say you have, say you have water and you want to make ice out of it. To make ice, you put the water in the freezer. So, we have our freezer here. We have a thing of water here, a bowl of water, whatever it may be. Now, the freezer temperature needs to be lower than 0 Celsius in order for this to get down to 0 Celsius. And if you think about it logically, to cool something off, you put it in a cooler environment than what it is. So for you to remove heat from the water, to get rid of the heat, and we'll talk about heat being Q in this chapter, to remove heat from the water, the temperature of the fridge must be less than the temperature of the water. If the temperature of the ambient temperature is higher, then it's going to warm it up. It'd be like taking an ice cube and putting it in a room. If you put an ice cube on a table, it's going to melt because they want to seek thermal equilibrium. Now, if 0 Kelvin is the lowest possible temperature, and you want to reach 0 Kelvin, then it doesn't make sense because you'd have to put it in something cooler than 0 Kelvin. And let's look at this for a second. Say you had an object, it does not matter what object, but say you had some object here, and you want to get this down to 0 Kelvin. Then that means that the temperature around it needs to be some negative Kelvin. But we just said a minute ago that 0 Kelvin is the lowest possible temperature. And for those of you that are familiar with this, we call it like a limit. Okay? It can try to approach 0 Kelvin, the temperature, as we get colder and colder, but it's never going to reach 0 Kelvin. Now, in laboratory experiments, they've reached temperatures that are, on the levels of, or the orders of 0.000001 kelvins. But, again, it's not possible to reach 0 Kelvin because the ambient temperature would have to be less than 0 Kelvin, which would make it a negative Kelvin. But again, by definition, this is what we call the lowest possible temperature, or no movement. So how could you have something that has negative movement? That doesn't make any sense. Okay, the next thing we're going to look at is heat. Let's start by defining heat. Now, your textbook defines heat as the energy transferred between objects due to a temperature difference. Okay, so due to some gradient, we call that in physics and engineering, a gradient or a change or delta in a sense. So there's some change in temperature between two objects, and that's what we think of as heat. Now, it's really important to know that heat can only move in one direction. Okay, heat and energy, or energy in the form of heat, can only move in one direction. And what I mean by that is the following. Think about it analogous to potential energy. You have a higher potential energy when you're up on a cliff, and you have a lower potential energy when you're down on the ground. And the desire, so this is a higher potential energy, and this is a low potential energy. If you think about it, you have a desire, in a sense, to want to fall, as much as you don't want to fall, but if you step off, you will move from a high potential energy to a low. You're never going to move from a low to a high potential energy unless you induce some sort of force or something that propels you upward. So, if you remember, high potential energy always goes to a low potential energy by default. You could think of it the same way as temperature. The higher temperature always transfers to the lower temperature. So if we draw an example, let's say we have a glass of water with some ice cubes. Okay? Let's say the temperature of the water is about 30 degrees Celsius. The temperature of the ice, we'll say, is -2 degrees Celsius. Well, clearly the water has a higher temperature than the ice, so what's happening is there's energy being transferred into the ice. Okay, people think, oh, the ice is making it cold. No, it's not actually. Ice is not making it cold. The ice is absorbing the heat from the water, which is by definition or by default reducing the temperature of the water. So maybe they meet somewhere in between, like we talked about. Maybe they're meeting at, like, I don't know, let's say 22 degrees Celsius. So as time goes on, the temperature approaches 22 degrees Celsius. Okay, so, at first it starts to melt a little bit, the temperature of water drops down to 29, then 28, then 27, until eventually it gets to 22 Celsius and the ice is gone. Well, there was only so much ice. If there was more ice, then it could have gotten colder. So that's going to lead us into something else we're going to talk about where we have, the mass involved. So if you have more mass, then we could realize that that could absorb more heat. So more ice, it could get colder. And we know that by common sense, but we'll see how that plays a role in our equations in this section. The symbol we're going to use for heat, okay, is Q. And I referenced that earlier. And the units we're going to use are joules. Okay, remember joule is spelled Joule. And this is our standard SI unit for heat. Okay, it's the same as energy. If you look at, for example, food labels and you look at a nutrition label, you'll see calories on there. Calories are energy. Calorie is just a different type. Okay, so for example, a calorie is equivalent to 4.186 joules. Now, when you look at nutrition labels, you're actually not reading calorie like that. You're reading this calorie, which is going to sound really weird. But calorie with a capital C, okay, it's used for foods, is really what's called a kilocalorie, which is the same as this number, but kilo meaning times 10 to the third. So when you see on the food label that it has, say, 200 calories, you have 200 of these, okay, not these. Even though we know in science to use lowercase calorie, okay, the capital calorie really means kilocalorie. All right. What we need to then talk about is the idea of conservation of energy. And how it relates to internal energy. So what we need to think about is the fact that mechanical energy is never lost nor gained, but it can be changed or transformed. And conservation tells us that the sum of the change in potential, kinetic, and what we call internal energy is always going to be zero. So if there's a change in one of them, it has to go somewhere. And the easy example would be this. Think about if you've ever hammered a nail into a wall. Okay? Here's the nail head. And there's the wall. The minute you nail the nail into the wall with the hammer, you might notice if you touch the nail head, the surface of the top of the nail head might feel a little bit warm. Okay? But what you're doing is you're applying some kinetic energy, and sure, it is, overcoming the force that's needed to break through the wall, so there is some change there, but you're also changing the internal energy. Okay? Try this at home, and be careful when you do this, but you've all probably done this already. Take a rubber band. Okay? Take a rubber band and stretch it. And what you're going to notice is that when you start stretching it, that middle region where it's getting really elastically stretched on the rubber band, so start with a normal size rubber band, and then stretch it, but be careful not to break it. You'll notice this middle region in here, you'll feel like a bit of heat. If you touch maybe touch the side of your face, your lips to it, you'll feel it changed in temperature. Okay, and it's no different than if you take a paper clip, and we've all done this one before. Take a paper clip and try and bend it open, so you bend it into a flat paper clip. And then start bending at about one point. So bend it back and forth. Bend it like that, then bend it like that, then that. Eventually it's going to snap in the middle. But what you'll notice is you'll feel there's heat. So you're putting in all this work. Where's it all going to? The kinetic energy that you're putting into it. Well, it's changing the internal energy, or it's changing the temperature of the paper clip. The next thing we want to look at is specific heat. And it's actually called specific heat capacity. Now, what specific heat is, it's by definition, you could see, specific to the substance we're talking about. And to make it simple, here's my example that I always think of. If you ever go to the beach in the summer, you might feel that the sand is really hot in the day. And then at night you touch the sand and it's really, really cold. But you'll notice the water during the day, sure, it's maybe, 78 degrees or 75 degrees. But then at night, it's only still 74 degrees or 75 degrees. It really doesn't change much. And we want to think about this. We want to think about the material or the substance itself and how the specific heat affects how its temperature can vary. And our general formula we're going to look at, and I like to write it like this. Your book uses a different way. I write Q equals MC delta T. Okay? MC delta T. And the variable that we're really looking for, specific heat now, and you'll clearly notice, is C. Remember, Q is heat transferred. M, we all know, is mass. And delta T is pretty obvious. It's the change in temperature. Okay, the change in temperature. So again, the specific heat itself is the value of C. And it's dependent upon the actual substance. Now, the easy way to think about specific heat, or its definition, is if we go ahead and solve for C. We'll have C equals Q over M delta T. And what we say is that the specific heat capacity is the quantity, or the amount of energy, Q, needed to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. If we look at this, if those are both 1, we get C equals Q. Okay, because we have C equals Q over 1, really. So C is simply the value Q needed to raise these both by 1. So if you set these equal to 1, what will Q become? That's what the question is asking. And that's what C is by definition. It's the Q needed when M equals 1 and delta T equals 1. And that's kilogram and degrees Celsius. Now, one thing we should really make note of is that the specific heat capacity of a substance depends upon the actual phase of the substance. The actual phase. So let's quickly talk about phases of substances before we go into how we determine specific heat. So first, substances we traditionally talk about have phases of solid, liquid, and gas. And if you talk more, you'll talk about plasma as a 4th stage, but for now we're going to talk about these 3 stages. Solid has a given shape, meaning a given volume, and a given structural alignment, and it does not change Whereas liquid has a certain volume, but it takes the shape of its container. Again, a liquid is defined as something that takes the shape of its container. So if you have water in a cup like this, with let's say 16 ounces, or water could be in a cup like this, and it could be 16 ounces, but you notice the shape changes. Gas has neither a fixed shape or volume. Gas constantly wants to expand. Okay? If you have a closed system for gas, say for example a balloon that you blow up, well sure, then it takes the shape of that, but the object itself will change based on the gas itself. Now, going back to determining the specific heat, the topic is called calorimetry. Okay, and calorimetry is pretty much a procedure that we use to measure the energy transferred from one substance to the other. And this allows us to determine the specific heat capacity. Okay, so this is used to determine the C value of some substance. You're going to notice your book, by the way, writes C as CP. And I should make a note of this because it is important. The specific heat capacity has to do with the pressure also. So when you see CP, they're just saying that it's the specific heat capacity when the pressure is constant. When the pressure is constant. Now, here's the whole theory behind calorimetry, and it's quite simple actually, and some people get confused, but we'll just talk about it real quick. Think about it this way. If there was some way you could have a fixed system, okay, an insulated system, if you will, so some boundaries where no heat could escape, okay, and you were able to, say, fill it with a liquid. Traditionally, that liquid is water. Okay? And then you put the object, in this case I'm going to put, I'll say it's, I don't know, copper, brown, copper. You put the object inside of the water. If you're able to measure the mass, and let's go back to our formula. If you can determine, or if you know the mass of the copper and the change in temperature of the copper, and at the same time, I'll write a different color here. Let's use orange. At the same time, you know the mass of the water, the change in temperature of the water, and we do know the specific heat capacity of water. If we know these variables, and we know that there's no heat escaping from the environment, we could say that Q1 must equal Q2. Because if we think about it, if the water is a high temperature, then the heat is going to transfer from the water into the copper. And the amount of heat that transfers from the water into the copper we can call Q1. And the amount of heat that transfers technically into the copper from the water, the same thing as Q2. So we could set these two equations equal to one another. And we'll notice that the only missing variable now, is this quantity C, okay, which is the specific heat capacity of the copper. So let's look at an example so that we can actually determine this. So we have a cup is made of an experimental material, or let's say unknown, of an unknown material that can hold hot liquids without significantly changing in this case increasing because they're hot liquids, its own temperature. Now, first of all, this is very, very useful because if you think about this, I mean, it's called the thermos, right? We think about a thermos all the time. If you want to hold your coffee in the morning and you don't want to burn your hand, you put it in a thermos traditionally. Not only does it keep it warm because it keeps the heat in, but it also doesn't allow that heat to burn your hand. Okay? Now, our goal is to figure out this specific heat capacity of the cup. So we're told that the cup's mass is about 3/4 of a kilogram. And has an initial temperature of 36.5 degrees Celsius. When it is submerged into 1.25 kilograms of water. With an initial temperature of 20 degrees Celsius. If they come to equilibrium, remember the same temperature, if they come to thermal equilibrium, at a temperature of 24.4 degrees Celsius, determine the specific heat capacity of the cup, okay, or of the unknown material. So let's think about an approach for this problem. Let's start with a diagram. First, diagrams are easy to draw. Just think about boxes again, right? Here's your water. And that's red, I know. And here's the cup that's submerged. Okay, again, remember, the heat is going to be transferring from the higher temperature to the lower temperature. So the cup has a temperature of 36.5. The water has a temperature of 20. So the cup has a higher temperature, so Q can be drawn outward from the cup. Again, the heat transfers from the cup to the water. Now, let's list our givens. We know that the mass of the cup, I'll say M1, we'll call the cup 1, and we'll call the water object 2. The mass of the cup is 0.75 kg. The specific heat is unknown. The initial temperature of the cup, Ti, is 36.5 degrees Celsius. The final temperature of the cup, Tf, is 24.4 degrees Celsius. Now let's talk about the water. The mass of the water is 1.25 kilograms. The temperature of the water initially is 20 degrees Celsius, and the final temperature of the water is 24.4 degrees Celsius. Again, notice the final temperatures are the same because it reaches thermal equilibrium. Now, the specific heat capacity of water is published, okay, and we can look that value up. But just to recognize that we're going to need it, let's take a look at what our equation looks like now. So our equation is the following. M1 C1 delta T1 equals M2 C2 delta T2. And again, why is this true? Because remember, the heat that is transferred from one object goes into the other object. Okay? Again, the the heat transferred from the cup, because the cup is hotter, goes into the water. And there's nothing where there's no loss of heat in a calorimetry example. The idea is that it's perfectly insulated. Okay, it's perfectly insulated. Now, we know that the only thing that we're really missing now is our value of C1. Okay, the specific heat capacity of the cup. This is the specific heat capacity of the water, and let's write that down. C2, the specific heat capacity of water, is 4.186 times 10 to the third. Okay, and remember the units, and I don't think we've gone over these units yet, but you can see what the units are if you think about solving for C in that original. If you go back, let's take a look back at our equation. Our equation said C equals Q over M delta T. So the value or the units of C are simple. Q is measured in joules, mass is kilogram, change in temperature is degrees Celsius. So those are going to be the dimensions of C. Joules per kilogram degree Celsius. So those are going to be the units that go up here with C2. Okay, I'm going to erase that so we work. Now, at this point in time, again, we're solving for C1. So just simply solve the equation. That's all we're doing now. So C1 is going to equal the entire right-hand side, M2, C2, delta T2, all over M1, delta T1. And now please notice that delta T's are different. Delta means change. So this C1 is really M2, C2. Now this is going to be final minus initial over final minus initial. Okay? Remembering that the numerator in this solution is really representing the water, because we know all the information about the water. We know its mass, we know its specific heat capacity, and we know its change in temperature. We also know the mass of the cup and the change in temperature, and this will enable us to determine the specific heat capacity of the cup itself. So let's see what we get as a number here. Plugging in, we have the mass of the water is 1.25 kilograms. The specific heat capacity, I'm going to write it as 4186, which is 4.186 times 10 to the third. Remember the units are joules per kilogram degrees Celsius. Times the change in temperature. And remember the final temperature was 24.4 minus the initial temperature. The initial temperature was 20 degrees. And these are both in units of degrees Celsius. I should really put that in here. Let me correct that. Hold on. 24.4 degrees Celsius minus 20 degrees Celsius. All over mass of the cup times, and let's look at our temperatures. We had final temperature is 20 degrees Celsius minus initial temperature of 36.5 degrees Celsius. Now, you're immediately probably saying, well, you're crazy because take a look at this, you're going to get a negative answer, and that is true. You will get a negative answer if you just do this. Now, one of the things your book says is it just uses delta T as higher temperature minus lower. What I like to do, and you can go back and show this in the formula, but I want you to see this before I actually input in the formula, is I think of this as an absolute value. Okay? Whenever you do your change in temperature, you're looking at the absolute value. Because really, remember how earlier, and I'm going to have to scroll up to show you this. It's going to get messy. Okay, remember up here, I'm pointing now, right up here, Q1 equals Q2. Well, what's really happening is, what it should really say is this, okay? But I didn't want to go crazy with the definition in your book. But one of the objects is gaining heat, and one is losing heat in a sense, okay? Again, the cup is losing heat, so it has a negative Q2 in a sense, or the cup is losing heat, so I should really put the negative here. Okay, and the water is gaining heat, so that should be a positive Q2. So if you go back and put the negative here, it'll alleviate that issue, making all these negatives. But you could also just do delta T as the change in temperature with an absolute value. So instead of doing that, you can just write it this way also. Okay, it really doesn't matter. Just know that your C value needs to be positive. You're not going to have a negative C value. Okay? But again, the real reason I like to say is simply because of the fact that one object is losing heat and one is gaining heat. Okay, whereas your book is going to tell you to do the higher temperature minus the lower. So what we're going to end up getting for C1, okay, in this problem will be, oh, you know what? I just noticed something. Go back real quick. This should be 24.4, sorry. Okay, why is that 24.4? Because it's the final temperature that both of the substances came to at the end, the equilibrium temperature. So the TFs need to be the same. So these values are always going to be the same as one another. So just make that quick correction. So anyway, your final answer you're going to get is 2537. And that's approximating to the nearest integer value. And remember, the units of specific heat are joules per kilogram degrees Celsius. And there's really a time symbol in between these two. Okay, so if you want to write it there. So this tells us that this is the unknown substance. Okay, let's do another question that uses Q equals MC delta T that will lead us into our next topic of phase changes. Okay, and how phase changes are affected by not only the heat that is applied, but also the phase itself. So first, let's think for a second. Let's say we have water, and because we used that in the last example, in water's specific heat capacity, as we said, was 4186 joules per kilogram degrees Celsius. And let's say we have a cup of water and we want to just heat it up, but we're not trying to boil it or not trying to freeze it. We're just going to go in one phase, so it's water. And we say that we want the water to go from a temperature of 20 degrees Celsius to a temperature of 70 degrees Celsius. And again, that does not go through any phase change. The phase changes of water occur at 0 and 100. And we know that the mass of the water is, let's say, I don't know, 0.5 kilograms. Okay, it's a good amount of water. So, given those values, let's say how much heat is needed to change this temperature, or how much heat are we going to have to apply to the water. So how much heat are we going to have to put on the Bunsen burner? Okay, and simply go to our formula, Q equals MC delta T, and simply plug in 0.5 kilograms, 4186 joules per kilogram degrees Celsius, times the change in temperature. My delta T is going to be 50 degrees Celsius. And take a look at your units. Conveniently, they must cancel out to make sense. So we have kilogram, cancels a kilogram. Celsius, cancels Celsius, leaving us with joules, our unit for heat. Okay, and what we'll get as a numerical quantity is 104,650. Okay, so approximately 104.7, coming around, kilojoules. Okay, that would be the heat needed to change water from 20 degrees Celsius to 70 degrees Celsius when the mass of the amount of water is 0.5 kilograms. And let's talk about this. What if the mass had doubled? What if there was 1 kilogram instead of a half? Well, then this was just double, which would make this double, which would make this answer double. What if instead of going from, instead of going 50 degrees up, we went from 20 to 45 degrees Celsius. So now the change is only 25 degrees Celsius. Well, that means that the delta T went in half. So this number here would be cut in half now. And this number would be just cut in half. So we need to know how the relationships work. And think about it logically. Go home and take a small pot of water and try to boil it to make, say, spaghetti. It might take you a little while. Take a big pot of water. It's going to take you a lot longer because you need to put a lot more Q into it, a lot more heat. It needs more time to absorb more of the heat from the flame so that it can actually boil. This is going to lead us into what we're talking about now, which is going to be the idea of phase changes. Phase change. Oops. I'm going to call it latent heat. And latent is, usually synonymous with dormant or stored. So we have to think about the fact that when we're changing a phase, we're not just increasing the motion of the molecules anymore. Because remember, in the last example, we changed the temperature from 50 or 20 to 70. That means that we're increasing the average kinetic energy. by definition, temperature is average kinetic energy, so we were just increasing the average kinetic energy. But now, we have to do something to the molecules within, and that's where the internal energy really comes to play. And we have to think about the fact that things are changing. It's physically changing. It's undergoing a physical change. Okay, so we're changing from ice to liquid, and then liquid into gas. And those phase changes are very different than the changes we see when we just add heat to change the temperature. We now have to do something to the bonds within the molecules. I'm just going to put it simply and try and summarize what is really going on in phase changes. And really what's happening is when you melt a substance and you go from solid to a liquid, the energy needed to do that is going into just rearranging the molecules. And there's a little more to it than that, but let's just say it's rearrangement. Whereas when you go from a liquid to a gas, what you're actually doing is you're separating the molecules. Okay, you're separating the molecules. Now, the energy needed to do these two processes or perform these two processes are actually quite large amounts of energy. And what we call these, okay, we call this the heat of fusion and we call this one the heat of vaporization. So I know vaporization. You always hear like, oh, you know, something got vaporized. And if you've ever seen the movie The Rock, he talks about, oh, he was vaporized. Vaporized really is not anything fancy. It just means that something goes from a state of liquid to a state of gas. Okay, it can be vaporized. So what I think of is this. Solid to liquid, this is, or back and forth, by the way. It can be either direction. It's a biconditional statement, if you will. Solid to liquid is freezing, in the terms of common sense or common terms, and liquid back to solid, solid to liquid is melting. Sorry, I'm backwards there. Solid to liquid is melting, and liquid back to solid is freezing. Liquid to gas is what we call boiling, and from gas back to liquid we call condensing. Like a condenser, okay? So again, liquid to gas is boiling, gas back to liquid is condensing, solid to liquid is melting, liquid back to solid is just freezing. And these two processes are different from one another. Again, one is rearrangement of molecules, one is more of separation. And they're going to have different values mathematically as well. So let's take a look. Our general formula we're going to use here for latent heat is actually quite simple. And the formula is the following. Q equals mL. And this is different. And let's compare the two formulas. Remember the last formula, Q equals mc delta T? Well, think about this. Q is the same. M is the same. That's heat transfer and that's mass. But what the difference is right here now. The substance has a specific heat and a change in temperature when it's physically changing temperature. But remember, when it's changing a phase, its temperature is not changing. And I want to show you that with a little diagram now. So let's take a look at a diagram before we go into these further. Let's take a look at water, for example, here. And let's draw a little axis. Okay, and we'll call this axis Q, or the amount of heat added. And we'll call this the actual temperature. We'll notice, I'm going to put 2 marks here. We'll do water again, make it easy. And we'll use temperature in degrees Celsius. So what we'll see is we'll add a certain amount of heat, certain amount of heat, certain amount of heat, till it gets to 0, which is the melting point. Then the object will start to melt. And we're going to add more heat. Then the object will start to boil. And then eventually it'll just be a gas. And what's happening here is the following. And I'm going to use a little tracer. You've got solid, solid, solid. You're adding heat. It's becoming, a solid at a higher temperature until it gets to 0. Well, when a solid, in the form of H2O, by the way, is ice, it starts to melt. And while it's melting, it actually doesn't change temperature. It stays at 0 degrees Celsius for a while. And it continues to melt, and it continues to melt, and it continues to melt. Then what's going to happen actually after that, once it all becomes liquid, it's all liquid here, then the liquid starts to heat up. The temperature of the liquid changes, the liquid gets warmer, it gets warmer, it gets warmer until it gets to 100 degrees Celsius, and then as we know, it starts to boil. And you'll see there's still liquid and there's steam. It's both phases, it's both phases, it's both phases, until all that liquid steams off or boils off into gas, and then it's all going to be gas. So what's happening is that there's a delta T here. There's a delta T here and a delta T here, surely. But look, this is a constant part of the function. This is a piecewise function. We have 5 pieces to the function. During pieces 1, 3, and 5, there is a delta T. But during pieces 2 and 4, this is, remember, fusion. This is vaporization. Those have no delta T involved because all that's occurring there is a change in phase. There's no change in temperature there. But there is change in temperature during the stage 1, stage 3, and stage 5 pieces of our piecewise function here. Okay? So what you'll notice is that here, to find the heat involved, we use Q equals mc delta T. And notice, though, this C is the C of ice. But then here in this stage, we're going to just use Q equals M. Let me rewrite that better. Q equals ML. L is what's called the latent heat of fusion. Okay, and we're going to abbreviate it with LF for latent heat of fusion, or the amount needed to change the phase. And back over here, now we're changing temperature. Q equals MC delta T. But again, notice this C now is the C for water. And they are different. Water and ice are different. Remember earlier, we talked about how C is a function of the phase itself. So C of ice and C of water are different quantities, and those are quantities that are measured, and we can find those in tables. Then we're back to stage 4 now, and we see that we're back to Q equals ML again. But now this is the heat of vaporization. So we call it LV. And L, again, L represents the latent heat needed to vaporize. And that's a quantity that is measured, and we can see that quantity in a table. And finally, the last stage, the Q needed to boil, is still MC delta T. But remembering that this C is the C for not just ice, not water, but now it's the C for steam. I was going to put gas, but let's call it steam, since water we call steam. So we have 5 stages, and the tough part is to think about, if you start with ice and you want to know how much heat is needed to get it to boil, you need to not only go through the temperature change here, you have to also go through this phase change, then more of a temperature change, then more of a phase change, then finally more of a temperature change. So these processes, when we calculate, can be very lengthy because we're looking at 5 different stages. Now, if we went, let's say, from a liquid to a gas, we'd be going from somewhere in here, change temperature from a liquid all the way up to here, then vaporize, changing the phase, then change temperature again to make it a gas. That'd be going through 3 different, in a sense, stages, not phases, but stages. Okay? So we have to think about where we occur on this graph when we look at examples. So let's take a look at an example of water. We'll say how much energy is needed. How much energy is needed to change, and I'm going to say H2O, because I want people to realize that's not always water. Change H2O from negative 15 degrees Celsius to 120 degrees Celsius if the amount of H2O is 4 kilograms. This is a tough problem. It's not an easy one again. We have to think about the fact that we're going from negative 15 Celsius, and we have to recognize what that is. Well, since 0 is the freezing point of H2O, that means that this is ice. And this here is above the boiling temperature, so this is gas. So if we think about it, we're going through all the stages. We're going to start as ice. We're going to melt into water. We're going to increase the temperature of the water. We're going to vaporize the gas. And then we're going to increase the temperature of the gas. So we're starting down here at negative 15 degrees Celsius. We're hitting 0 Celsius. we're hitting 100 Celsius, and then we're finishing off at 120 degrees Celsius. So this is the process of which we need to undergo. So this is quite a lengthy process. Let's take a look at what we've got. We really need to start by listing our givens. So we need to know what the specific heat capacity of ice is first. And that's given in our table. It's on page 372. Ice is 2.09 times 10 to the third. And all of these units for specific heat are going to be joules per kilogram degrees Celsius. The specific heat capacity of water, as we said earlier, is 4.186 times 10 to the third. And the specific heat capacity of steam is given as 2.01 times 10 to the third. Okay, so they're clearly different numbers. Now, we also need to know our latent heat of fusion and our latent heat of vaporization. And what we'll get, and this is on a table on page 379, and they list this as water, by the way. It should say H2O for substance, but they always list it seems to be the liquid form, but we call it water. I would call it H2O, table 10.6. The latent heat of fusion, meaning the amount of energy required to go from a solid to a liquid, is given as 3.33 times 10 to the fifth. I'm going to go over those units in a second. And the latent heat of vaporization, meaning to go from a liquid to a gas or a gas back to a liquid, is given as 2.26 times 10 to the sixth. So clearly we're going to notice, first of all, let's make some key points here, notice some things. It takes more energy to go from a liquid to a gas. Look at the unit, look at the order, 10 to the 6th, than it does to go from a solid to a liquid. This is on the order of 10 to the 5th, this is on the order of 10 to the 6th. Now, to determine what these units are, it's actually quite simple, and I'm going to show you an easy way to do it. Just go back to your formula. Q equals mL. Solve for L. L equals Q over M. Well, the units of Q are joules, and the units of mass are kilogram. So the units for LV and LF, the latent heats, okay, at the bottom down here we're talking about, the units of latent heats are joules per kilogram. So now that we know all these values, those are our first givens, okay? I'm going to erase the right-hand side now so we can use this. Okay, now, let's remember that we went from negative 15 Celsius to 120. So we have to think first. We go from negative 15 to 0 in the form of ice. Then we go through fusion. Then we go from 0 to 100 in the form of water. Then we go through vaporization. And then we go from 100 to 120. So let's take a look at the 5 pieces of this formula we're going to need. So what we're going to have to do here is look at the total Q of the entire process and think about it as the sum of all the energy needed throughout this entire process. Now, there are 5 stages of this process: Q1, Q2, Q3, Q4, Q5. Each of these stages having to do with different parts. So let's write them all out. First, we have the mass times the C of ice times the first change in temperature, and that's going from negative 15 to 0. Then we have M times the latent heat of fusion. Then we have M times the C of water, times the second change in temperature, and that's from 0 up to 100. After that, we have M times the latent heat of vaporization. And then finally, we have the last part, which is M times the C of steam times delta T3, which is really from 100 to 120. Let's factor out the M and call the C's 1, 2, and 3. So let's write it like this. So again, I'm factoring out M out of all these terms. And I'm going to list my C's respectively as 1, 2, 3. So C1 delta T1 plus LF plus C2 delta T2 plus LV plus C3 delta T3. Okay? Remember, C1 is ice, C2 is water, C3 is steam. And at this point in time, we can take that equation and just plug in our numbers. And at first, it seems like, well, do the units match up? But they actually do, and we're going to go over that. So, using our given values, Q equals 4 kilograms to start. Units of C are going to be joules per kilogram degrees Celsius. The C of ice, as we said a minute ago, is 2.09 times 10 to the third. So we'll write that as 2090, okay? And its units are joules per kilogram Celsius. Times the change in temperature. Well, we went from negative 15 to 0. So let's just put a change in temperature of 15 degrees Celsius. That's the first part. Plus the latent heat of fusion, which is given in our book as 3.33 times 10 to the fifth. And its units are in joules per kilogram. Plus, to that, we need to now look at C2. The specific heat capacity of water is 4186 joules per kilogram degrees Celsius times the change in temperature. And that went from 0 degrees, we're looking here now, it went from 0 degrees to 100 degrees. So that's a change in temperature of 100 degrees Celsius. Plus the latent heat of vaporization, which we were told a minute ago, that was given as 2.26 times 10 to the 6. So 2.26 times 10 to the 6. 2, 3, 4 zeros. The comma's in the correct place. Okay. And this is units of joules per kilogram. And then finally to that we have to add the last portion, which is when it became a steam, but it went up to 120 degrees Celsius. And the specific heat capacity of steam is 2.01 times 10 to the third, or 2010 joules per kilogram degrees Celsius, times the delta T. Now this went from 100 degrees Celsius up to 120 degrees Celsius, so the delta T was 20 degrees Celsius. And that's our actual answer. And what we'll notice is this. It's the cool part to see. We see that units start canceling everywhere. Cancel, 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 cancel. Leaving everything's units of joules per kilogram, but the outer unit of mass is kilogram. So this outer unit of mass of kilogram cancels all of these kilogram units, leaving all of the units to be joules, just as we had suspected, because we're looking for the energy needed. And let's take a look and figure out what our total comes out to be for this. So for this value, we end up getting a total of 3083150 joules. And I don't know if anybody knows, but this 0 seems to disappear. There was a 0 here. Just correct that if not. 333,000 there. And now what you'll notice, and one thing I want to point out here, is that this is on the order of around 3 million joules, where the latent heat of vaporization was already like 2.25 million joules. So this is what takes up most of the energy, and this takes up a ton of energy, I would say. Then the big temperature gap, or big temperature change, takes up a lot of energy, and then these two, temperature changes don't take up as much energy. So the last thing I want to talk about in this major section for heat is the modes of heat transfer. And there are really 3 modes. We're going to talk about 3 of them. The first one's called conduction. what conduction really is, and the easy way to think about this, is that two surfaces have to be in contact. Okay? And like, doesn't necessarily mean that the surfaces are things that we can touch, but like air in contact with glass is by modes of conduction. But there has to be some contact between them. Now, conduction is extremely, extremely important, and it is used widely, mainly in insulation. And we'll talk about insulation in a second, how that works. But the easy way to think about conduction is as follows. Imagine if you were in, let's say, a classroom. And here's the whiteboard, and then you have this ledge here with the whiteboard markers. Okay, and the ledge is made of metal. Alright, so it's a metal ledge, and let's say the whiteboard around it has a wood panel. Okay, there's a wood frame. So this is wood, and this is metal. Now, we talked about thermal equilibrium, and if this is a classroom that's been, in existence for a while, the temperature in the room should be consistent throughout the room, at least, between the wood and the metal in that area. But if you try it sometime, and you'll really notice this, and it's kind of a weird thing people don't think of. If you touch the metal, it feels like it's colder than the wood is. It really does, but it's actually not, and that's the key here. And what's going on is this. Wood and conduction is all based on, by the way, what's called a K value. It's called the conductivity. Okay, this is different from the K value with springs, where that's the spring stiffness. The K value is the conductivity, or the rate at which energy can really be transferred. That's what it's thinking of here. The K value of wood is much lower than the K value of metal. So because the K value of metal is higher, it means that when you touch the metal, the heat from your hand transfers very quickly into the metal, making it feel as if it's colder. Because, again, the heat is flying out of your hand into the metal. So you feel that change in temperature. So you're going to feel like it's really cold there. But with the wood, you don't feel it as much because the K value is very different. And the other example of this that's perfect is double pane windows. The way double pane windows work is as follows. So we're going to look at a profile view. So let's say, first of all, here's a window. Okay? You lift the window up, you put the window down. Now let's take the window and turn it 90 degrees. Now we're looking from the side view. So here's a pane of glass. Here's another pane of glass. And the window unit is connected here and connected here. The window can lift up and the window can lift down. So we're looking literally from the side in now at this window. So what you have here is air or some sort of gas between the two pieces of glass. So again, glass, glass, and gas. Traditionally, I think they use argon. It might have changed, but last time I checked it was argon, because of the fact that the conductivity value, K, of argon is so low. Now, what this means is that it acts as an insulator. So, there's this cold air out here, I'll say 30 degrees Celsius out here, or let's say 30 degrees Fahrenheit for the sake of this. And you're inside the classroom and say it's 75 degrees Fahrenheit, so it's a cold day in the winter. But in the classroom, it's nice and warm. What's happening is the heat from here, again, wants to move from hot to cold, so it wants to get through here. And it can easily get through the glass. It flies right through the glass, because glass's K value of glass is very high. But then it hits this barrier of gas, this argon barrier, which kind of slows it down. And if you zoom in on this, and we look at the three barriers, it goes very quickly through the glass, but then it slows down when it goes through the argon. But then it can speed up again through the glass. But this barrier right here is what produces that insulation and what stops it from actually transferring the heat out of the room so quickly. This is also very similar a thermos. Think about a coffee cup. Normally a coffee cup looks like this. But if you have a thermos, and a good example is a brand, and not that I'm pushing this brand, I don't know it's stocking or anything, but Contigo. Contigo makes phenomenal thermoses. They can last, you put hot tea in there in the morning, it will be hot for 5 or 6 hours straight. Put cold juice in there, it'll be cold for 5 hours. Because there's a great wall of insulation in here. And this insulation is made of a material that does not have a high thermal conductivity value, K. It does not conduct heat easily. So it keeps the heat in if it's hot, and if it's cold, it keeps the heat out to keep it cold. And it's a Contigo mug, and then there's a lid, obviously, on the top that goes on top. Okay, but that's the idea of an insulator. And this is conduction. Remember, conduction has to do with two surfaces being in contact. Okay, in contact. The second and third modes of transfer we're going to talk about quickly. One is called convection, and one is called radiation. Okay, and this is electromagnetic radiation, really. Convection is pretty complicated, actually. It has to do with pressure differential. It actually has conduction involved in it. There's buoyancy involved from fluids. But the idea is this. It's the idea of displacing something that's hot with something that's cool. And convection traditionally occurs where there's a fluid flow over a surface. And the good or prime example of this is if you try to, or if you have what's called like a supercomputer that has a supercooler in it. And in a computer system, you've ever heard of what's called nitrogen cooling. And it's like a liquid cooling system where there's the CPU. And usually the CPU has a heat pipe attached to it. And the heat pipe can transfer heat to a heat sink, which has fins on it. And that heat sink can give off heat. And this is usually done through conduction now, right here. But in other types of computers, what they'll do is they'll run these cooling elements, and there'll be fluid that flows around it. And you'll run like liquid nitrogen over here. And that liquid nitrogen, as it runs over the surface, will absorb the heat from the CPU in order to cool the CPU down. It'll then run through another cycle, cooling the liquid nitrogen back off using some sort of electrical pump and cooling unit. Then it'll come back through the cycle again. So it runs this coolant over it, and like a refrigerant almost, like a refrigerator would do. But the idea of convection is traditionally that you have a fluid flow over a surface. Okay, fluid flow over a surface. The last type of heat transfer is radiation. And really what radiation is, again, it's electromagnetic, but this doesn't really involve transfer of matter. Instead, what it does is it involves the internal energy. And what happens is it takes place from high to low temperature. And what it does is it kind of emits radiation off. And you've heard of radiation before with the sun. Don't get too much radiation, or you could be exposed to radiation like gamma rays or radiation with nuclear radiation. And it has to do with a core that might be hot, and it's emitting these electromagnetic waves from some central object. Some EM waves are coming off at different wavelengths, and it's giving off heat. And what that does as a result is it cools off the core. So it gives off heat in that form. And the easiest example is just the sun emitting its rays. Okay? Those are mainly the three forms of heat transfer.